with first integrated equation one to express the density law in terms of n. After doing that, we choose an approximation of ignoring higher than 0 in this equation, which is usually valid with this to come up high temperature parameter regime. And if you do this and then insert it results in expression to the second equation, then you can eliminate all of those, then convert this equation into second order differential equation for m. Then I intentionally wrote the equation in this form because it looks like Newton's equation motion. So let's try to now use this here to understand what that means. So I basically have Newton's equation of motion with damping, damping coefficient gamma, and some potential profile. And then one thing you can see, we can show is that if you have this kind of configuration of droplet having higher density, and then the overall background having lower density, then I can show that the potential value inside of the droplet is going to be higher than the potential value outside. So it means if I try to distribute this profile from the droplet side to the outside, then I'm basically considering motion of some particle, which is falling down from higher density points where n and the value of n is higher, and then it goes down here as I'm going through this interface, and then settling down in this magnetization value outside the droplet. So if this motion is upward, then I will be able to find the interface profile. So in order to realize that, I need to lose energy. If there's energy conservation, it won't be possible because the are not the same. So which means that my damping coefficient has to be larger than 0. And then in order to make it larger than 0 with this setup, my C, the interface speed, the speed, has to be larger than V, which means that the front interface of the droplet is going faster than the spin speed. So this is one mechanism which is enabling droplet growth. The front is going fast. And another thing I can also show is that when C is equal to V, then we are going to have gamma is equal to 0, and then the droplet will begin overshoot. And then as I'm increasing V to really, really large value, V becomes symmetric on the droplet side and then outside. And then this gamma is going to become large. So I will just set it down to this minima to other high point. So by continuation between these two extremes, I can argue that there will be some value of C between V and infinite, which is enabling connection between these two very high points and then giving me the solution for the interface. So with this, we calculated the interface speed analytically and then compared it to the value observed from simulation. So there are three interfaces usually happen if you have a look at the scan configuration that I showed before. So here I'm showing you the front interface speed and then the rear one, but which is going together with the droplet, and then the other one which is repeated. And then these solid lines are very expected interface speed that we calculated through this procedure, and then the symbols are simulation result, which already had published. Okay, so the difference between the front interface speed and the rear interface speed indicate that the droplet size is actually growing, and this is the mechanism enabling droplet growth. Now, let me show you what is the implication of this family. So to do that, I will compare two time scales as compared to system size. So I'm going to indicate the time scales out. So one is that where previously asked what happens as you are going to a large system size, can you do we encounter any kind of finite size effect? We don't really see that, but instead what you usually see is that there are more frequent droplet excitation, and then the average time between the droplet excitation event increase with system volume. So this is one trend in the time scale. Another thing I can say is that once the droplet is excited, and either goes through system, try to convert the whole order along the droplet order, and this kind of worsening time has to be larger than has to be has to increase at least with the system size to the first order or even higher because there will be some diffusive process required in the later case. So the competition between these two time scale depending on the system size, I'm going to encounter somewhat different phenomena. When system size is small, I'm going to encounter layered droplet excitation event followed by fast coarsening. So which means that the order phase will calculate in very fast. Truly where larger system size may be more than what I'm going to encounter is that the droplets will be excited in several other locations, and then none of them will have chance to really coarsen the whole system, and therefore I'm going to see very crowded droplet phase, and then therefore there will be no shorter. It is part of this relation. Right. Another thing is that the mechanism I explained is not really constrained to 2D. Indeed, if I perform activating with a simulation in 3D, and then see what happens if I insert the droplet, it grows, and then it will do so more and more in higher dimension. And therefore, this is indicating that the clonage order in activity model is processed down. Okay, so considering the time. So it's all right to answer the questions. Nice. Okay. Now I will briefly highlight what happens if you insert the droplet in the blocking model with continuous symmetry instead of discrete symmetry. So uh, without we're introducing more words, I will directly show you the 2D. So here I'm again showing some microscopic simulation. And in here, now I'm not considering activity model anymore. I will consider the continuous orientation version of the activity model. So the spins are having now continuous orientation. And then again, I prepare order phase by letting the spins float along the minus x direction. And in there, I insert the center of it. And then if you see what happens, in the case, the alignment strength of the spins are not strong. This is what I see. So because the spins are now able to go along one direction, it doesn't show me droplet. It forms to propagate. And because I'm putting periodically bounded condition, the wing of the droplet was coming in. But what it is indicating is that maybe similar droplet excitation event is happening here, and then maybe the continuous symmetric growth is also subject to similar stability mechanism. However, that's not quite the case because if you increase temperature further, increase the aligning strength more and more, then no matter how large the droplet is or the droplet density is, it eventually will experience evaporation event that you see here. There's something different happening as we are moving on to floating continuous symmetry. So I will briefly highlight 1.1 here and then. Okay, so start from the magnetization profile that you see. So again, let me scan through one specific line along y-axis at some certain value of y, and then go to the x-axis. Then let me make it that I prepare it in the x direction of magnetization, just like activism. So here, one thing I can see is that there are regions where the states are predominant aligned along just that direction, and then other states which are aligned along negative direction. And then at the interface, in the middle, there is a region where the x direction of magnetic goes to 0. And in here, now because of the symmetry of the system, the magnetization can not only have direction of as well. And then basically at this point at the interface, I'm looking at the spins which are placed on top of this alignment at the top of the alignment potential, and then it is having instability to fall down to anywhere. So previously for activism model, the spin only have choice of falling toward plus mx direction or minus mx direction. If it goes to minus mx, it will the spin will go even deeper droplet and eventually surrender and join droplet. If it goes to plus mx direction, it will just yeah, it means that it already joined the droplet. So that is the scenario you see in the case of the activism model. However, in the case of the prime heritage case, we also have choice of falling down for y direction. So because of this, when you have a look at the time evolution of the y direction of the magnetic maybe after some time scale, it's given by one over flipping rate, there will be some excitation of y direction of magnetic. And then if this can grow significantly, then the interface is will enter some tissue because it will gradually accumulate some spin which are tilting toward y direction and then destabilizing the overall interface shape. And this time scale argument can be tested into the length scale argument as follows. So here there are two length scales competing with each other. One is interface based, where this kind of where this kind of instability kick in, which is given by the ratio, which is diffusion rate and the propagation rate. And another length scale, important length scale is the non-length, which is given by propagation rate divided by diffusion rate. And if non-length is larger, much large compared to interface width, then spin will be able to go through interface without undergoing flipping events. So this mechanism will not be. However, if the non-length is much smaller compared to the interface width, then the spins will start to flip and then induce some instability in the alignment or the y direction. And this can lead to the disruption of the interface, of the droplet interface that I showed before. And then in the because of this, the composition of non-length, L is equal to proportion to the flipping rate, and then flipping rate increases as you're decreasing temperature. The alignment strength is always lower, and this means that L decreases as T is lower, and then eventually the instability of the interface will decrease in low temperature. That is basically the penalty. Okay, so with that in mind, we revise what is the expected stability equilibrium active model, specifically for polar protein. So for a model, active polar protein model with discrete symmetry, hopefully I convinced you that there would be long range order in thermodynamic dimension. And then for I have to invite this out of the comment video, but for the floating model with continuous symmetry, there's another mechanism which is destabilizing the interface in here, and then therefore over to be restored. And for now, until another mechanism kicks in, and we can probably say that there seems to be continuous stable moving order. With that, I acknowledge that this is work with traffic of Rio, of Alex, and the owner who is in Chicago, and who is now in Tel Aviv. What's interesting? Thank you very much.